A very good afternoon and welcome to this webinar on measuring and monitoring short-lived climate pollutants in the solid waste sector. This is a part of the ongoing series of webinars under the Climate and Clean Air Initiative CCAC. The CCAC was launched by the UNEP and aims to catalyze rapid reductions in short-lived climate pollutants to protect human health, agriculture, and environment. Today's topic, measuring and monitoring short-lived climate pollutants in the waste sector, assumes great significance behind successful monitoring of pollutants such as methane and black carbon in the solid waste management space, especially considering continuing practices of open burning of waste on curbside, leading to generation of black carbon. To take us through with more on this, we have with us Professor Brajesh Kumar Dubey from IIT Kharagpur. Professor Dubey brings with him 16 years of rich research, teaching, training, and industrial outreach experience in the areas of solid and hazardous waste management. He has been teaching courses on solid and hazardous waste management for nearly a decade. He has authored more than 200 publications in his area and taught in several universities in USA, Canada, China, and India. So we will start with a 45 minutes presentation from Dr. Dubey, followed by a question and answer session. You can send us your questions during the session or post the presentation using the small chat box on the right-hand side of the page. With that, I'm going to enable the audio for our expert for the day and turn things over to Professor Brajesh Kumar Dubey. Professor Dubey.
So yeah, good afternoon again. So we are going to have a webinar right now on measuring and monitoring what happened here? Okay. So we're going to have a webinar on measuring and monitoring short-term climate pollutants in the waste sector. So as part of this webinar, the way I have has it designed, why is it not? Yes. So I'm going to have a quick review of the climate change, like what's the climate change is all about, and what we are going to talk about in terms of the climate change. Then we'll look at the potential climate pollutants in the waste sector, because this webinar is focused on the waste management sector. Then we talk about a little bit of measuring and monitoring methods. What are the measuring and monitoring methods, as the title suggested? Some case studies of a few of the landfill sites which has already been done in India, and we'll talk about that. And then towards the end, we'll also look at that when we collect data in this sphere, there are a lot of data uncertainties, how to manage the data. So we'll kind of summarize that aspect and then close this webinar. So with that, we'll get started. And in terms of the waste management, as we know in Indian practices, as most of us probably are aware, that typically the way we manage the waste, we try to, as per the regulation, we say that we'll try to treat the waste, but nearly 70 to 90% of the waste is still going to open dumping. And many of those dumps are not even engineered landfills. So there are some engineered landfills, especially from the Indian context, and also in many developing countries, the situation is similar. Developed countries, they have that engineered landfill out there. And other than in terms of open dumping, other things that is happening is composting or anaerobic digestion to some extent. Then there is a lot of push on waste to energy, especially if you look from a Indian scenario. We are also having waste to energy push recently. So some waste to energy plants are coming up. So all these activities does generate certain pollutants. So when we talk about landfill, landfill initially is an aerobic process, then later on and gradually moves towards anaerobic system. So when we are in the aerobic system, we're talking about carbon dioxide. When we move to anaerobic, you're predominantly methane, and then also CO2 is there. And composting, you could have CO2, you could have N2O, you could have a carbon monoxide coming out. When you go for incineration, again, CO2 and other things are there. And one of the biggest problem that we are facing today, which Kaushik just mentioned in the introduction as well, is that open burning of garbage. Open burning of waste, those of you who are familiar with what happened in Delhi recently, I think a month ago, and in that area, because of the open burning of agricultural waste, that creates a lot of particulate matter, black carbon and all that. So we'll try to define what is the long-term climate pollutant and what is short-term climate pollutant in terms of, and what are the short-term climate pollutants from the waste sector, and we'll try to give some examples along that line. So landfill, as this most popular and economic method, is still 70 to 90% of the waste in India is going to these open dump sites and creating a lot of pollution in terms of land pollution, water pollution, as well as the air pollution. And the dump sites have potential contribution to climate change, as you will see that all different types of contaminants that we're going to talk about, they do generate to some extent from these dump sites, either through uncontrolled burning or through different activities that is happening. So as the title suggested, climate change, I assume that most of the audience will be familiar with that, but just for the sake, what is a climate change? Like climate change, the Earth's climate has gone through many changes over billions of years. So it's as we can see, even this particular winter seems to be more cooler, even in West Bengal, where I'm sitting right now, than what it was last year. And if you followed the news in Florida, we had snow this time after maybe 33 or 4 decades. So there is a change in climate, and there is some people we use the term global warming. Some people say global warming is not because it's not only warming, it is also cooling. So warmer areas are getting warmer, cooler areas are even getting further cooler. And there is a change. Rajasthan gets flood, and then where it's supposed to rain, we don't get that much of a rain. So there is overall there is a change in climate, and that keeps on happening every, say, thousands of years or millions of years, whatever. But what we are concerned about is that because of this improper solid waste management, what are the type of pollutants that we are generating? And that's where our focus will be. What are the short-lived and long-lived climate pollutants that is there? So what is the short-lived climate pollutants? What is the definition of that? The short-lived climate pollutants, essentially, they are, as the name suggests, they are short-lived. I'm sorry for the spelling mistake on this title over here. It should be SHORT. It's not. Sorry for that. So it's a short-lived climate pollutants are the ones which it stays in climate for a shorter period of time, as compared to the longer-lived climate pollutants, which is carbon dioxide. So their relative potency is pretty high. It can be tens, hundreds, or 1,000 times higher than the CO2. And why we are getting this attention on short-term climate pollutants in recent times is, as we know that carbon dioxide emissions are responsible for nearly 55 to 60% of anthropogenic radiative forcing, which is the term used for measuring the impact in terms of the climate change. And what is we need to manage that CO2, but at the same time, the other 40 to 45% of the global warming effect or the climate change effect is coming from these short-lived climate pollutants. And although we have been aware of these short-lived climate pollutants for nearly 3.5 to 4 decades now, but in recent times there is a renewed interest because what we found out is that we have already added enough greenhouse gases to warm the planet by more than 2 degrees centigrade during this century. So some of the reductions of this climate change is happening because of the cooling aerosols, primarily sulfates, which are reducing under current air, which are being reduced under current air pollution policies as well. But these are important, but they will contribute to the near-term warming as well. So unless we start looking at these mitigation of SLCPs, as we call them, short-lived climate pollutants, there is a chance that we may cross 1.5 to 2 degree threshold by even mid-century. So that's why the reducing this SLCP is becoming becoming an effective strategy for constraining the warming in the near term. So in the short term, we are trying to focus on that. And other thing that as you will see as we make progress, that this SLCPs which are out there, which is black carbon, methane, tropospheric ozone, we'll go over each one of them in a bit detailed, and hydrofluorocarbons. So 3 out of these 4 are also known as air pollutants, and they are air pollutant in terms of damaging of public health, damaging of ecosystem. So reducing them not only impacts the climate change, but also prevents millions of premature deaths every year. They can protect millions and tons of crops and contribute towards sustainable development. So it's a food security issue as well, and of course the human health and public health issues. Then what has been seen that if you take action on these pollutants, it's more localized effect rather than global effect. So it's the benefit for the health, crops, and sustainable development. It actually happens primarily in the nations or region which take the action to mitigate this. So it's a stronger impact in terms of black carbon and tropospheric ozone have near their emission sources. So if you can try to control them. And there are technologies out there. There is a recognition that there are practical and proven ways to reduce these pollutants, and there are laws, there are institutions. So why not to take the advantage of this and try to support the reduction of SLCPs? So these are the 4 SLCPs that we'll be talking about in this webinar. And compared to them, the long-lived climate pollutants is carbon dioxide, which we all are aware about. Most of the time when we talk about climate change, we focus mostly on CO2 emissions or equivalent CO2 emissions coming from these other sources as well. So if you look at different, like out of these 4, if we can just have a quick review of what are these 4, how they have different types of impact on human health and environment, and then we'll talk about how to measure them as well. So black carbon, why we worry about black carbon? Again, anything is always better to understand like why it is it's a problem. So in this case, in terms of the black carbon, it's a potent climate forcing aerosol. It remains in atmosphere for only a few days a week. So it's as you can see, the lifetime is only a few days. It's only a few days it's available, and it's component of soot, and it's incomplete combustion of fossil fuel, and even for the burning, any burning when you have incomplete combustion at say burning at a low temperature, as you can see on the pictures over here, and that creates this black carbon, and they do contribute to climate change in several ways. It warms the atmosphere. How it does that? It absorbs solar radiation and emit it as a heat. It contributes to melting by darkening the surface of ice and snow when it is deposited on them. And it also affects the microphysical properties of clouds in a manner that can disturb the precipitation pattern. So there have been some estimates, recent estimates. They found that black carbon's radiative forcing is the second leading cause of global warming. So it's very close to like it's almost 2/3 of what we see from CO2. So and on the other hand, as I was saying earlier, it also harms human health. It is a primary component of PM 2.5, which is the particulate matter. We hear a lot in terms of the air pollution. So what it does, it can contribute to adverse health effects, including asthma, respiratory problem, lower birth weight, heart attack, lung cancer. So those are the causes in terms of impact that it has. And it's mostly local and regional impact, and global impact is less, as you can see from the different stars, basically telling you the different level of impact. So kind of quantification has been kind of presented using those stars there. So the source is mostly open burning. It could be open burning of biomass, open burning of solid waste, diesel engine, residential burning of fuel. So they also cause like a black carbon production. And then agricultural residue, which we saw a lot in recent times. Every winter we do that in the north, especially in Delhi region. So it has been it's co-emitted with other pollutants as well. So there are other pollutants along with it does get co-emitted. We'll talk about how to control them after we introduce all these 4 pollutants first. Then we'll go into control of these different pollutants. So in terms of the source, if you look at on-road diesel transport, again, you saw the picture of the diesel vehicle there. That gives black carbon emissions of nearly 15%. Your residential wood combustion, home firewood burning, which is again a big thing happening in many parts of the world, including in India, in the rural, especially in the rural or the slum areas. And during winter months, probably everywhere on the side of the road, you see happening that. Upstream petroleum industry, rail transport, other transport, and then there are other sources. And then you have here off-road diesel transport. What does that mean is all that different types of diesel used for, not for transportation part, but also for the others. Like for example, you are using it in an agricultural field for those gensets. Even many malls are being used being run on diesel like gensets. So those are also causing black carbon emission. So second pollutant that we are talking about is methane. Again, its lifetime years is around 12 years, so it's slightly more than a decade. And it does have a global impact. Local and regional impact is there, but it also has a global impact. That's the methane we always talk about. It's a powerful greenhouse gas. If you take the 100-year global warming potential, which is as per the IPCC protocol, it's nearly 20 to 25 times that of CO2. And its atmospheric lifetime is around 12 years. And 60% of the global methane emission is due to human activities. And those, when they say human activities, landfills, wastewater treatment plants, those are actually one of the major source of methane, because the fugitive emissions from these, many times our, especially the dump sites, we don't have proper gas collection system, so methane is just getting exposed to getting released into the atmosphere. And in the other places as well, where we do have a gas collection system in the developing world or some with the engineered landfill, still there are gas collection efficiencies only around 50 to 55 to maximum 60-70%. So in that case as well, we have nearly 30 to 40% of the fugitive emissions. So, and that contributes towards the methane emissions into the environment. And so that's the cause of methane. And then agricultural activities. Then we also have from the livestock. That's again another source of like a methane being emitted into the atmosphere. So if you look at the different sources, we have oil and gas fugitives from the oil and gas industries, oil and gas venting, this is fugitive emission. This is what has been done as part of the process. Then we have agriculture, nearly 27%, landfill 24%. So if you look at landfill, nearly 1/4 of methane emissions happening in the world is from the landfill. So that's a huge chunk of methane getting into the atmosphere through our waste management activities. So then hydrofluorocarbon, which is another like it's a factory-made chemicals. It's primarily used in refrigeration and insulating foams. They have a warning effect of hundreds of thousands of times more powerful than CO2. Average lifetime of the mix of HFCs is nearly around 15 years. That's the weighted by usage. It's one of the fastest growing greenhouse gas in many countries, including say United States and others, where emissions is growing between 9% as compared to 3.6% for CO2. Globally, these emissions are growing at 10 to 15%, and it is expected that by 2020 we'll have double of what we had in 2010. So we need to control that the growth. By 2050, the annual climatic forcing of HFCs will be actually equal to 20% of the forcing from CO2. So 20% of the climate impact that we're getting from CO2 right now, that much impact will start seeing from HFCs if we don't control them based on the present rate by 2050. So there is there has to be control in terms of the HFCs, and if you look at the different sources, it's mostly refrigerations, air conditioning, aerosol foams, and others. So that's where we are getting most of the HFCs are coming into the environment. So, and then the other one that we had, the last one in terms of the 4 short-lived climate pollutants, is the tropospheric ozone. So this tropospheric ozone, it's not, it doesn't get released. It's not emitted directly, but instead it forms from the reaction between the other precursor gases, which we'll just explain. And those precursor gases gets released as part of the waste management activities. So here you see some of the sources of precursor gases which are coming out, including from waste management activity, from industrial process, other diesels and other stuff coming out. So it's those precursors, especially including carbon monoxide. As you can see, carbon monoxide, it's a human, and these gases could be both human produced as well as natural. So it both is there. So it's carbon monoxide, oxides of nitrogen like NOx, and then volatile organic compounds, which including methane. So these gets released, as you can see, from cities. We have NOx and COs and VOCs, and forests we have VOCs, power plant we have NOx, then ammonia and others. So all these, when they react together in the presence of sunlight, they produce ozone in the troposphere. As we know that ozone, we do need ozone. Ozone does help us in terms of in the stratosphere, in terms of keeping those harmful rays away from the Earth. But at the same time, when it's in the troposphere, what it does is it absorbs dangerous in the stratosphere. It absorbs dangerous ultraviolet radiation. But when in the lower atmosphere, ozone becomes a major air and climate pollutant. So it causes warming, and it's harmful to human health and crop production. So if we breathe ozone, it's particularly dangerous to children, older adults, and people with lung disease, and can cause bronchitis, asthma, and can have an impact on lung tissues. It impacts plant, not only lower crop yield, but also has a reduced ability of absorbing CO2. So it does impact them. And so this is how they get released and they get formed. And as you can see from here, the VOCs, carbon monoxide, they are all ammonia. These all could be released from the waste management activity. So that's where we are looking at in terms of different soft-lived climate pollutants essentially coming from waste management related related tasks that we do. So how we can control in terms of residential sector, we can replace traditional biomass cook stove with modern electric cook stove. So that's one aspect. Industrial sector, for brick kilns can be moved with a more improved kilns. So those things are there. Transportation sector, it can eliminate high emitting diesel vehicle. So recently we also had the diesel car were banned in Delhi. So that's could be one stuff. At the same time, we should ban all those diesel running electrical gensets. Those generators running on diesel should be banned. And at the same time, why should we have even allow those big SUVs running on diesel? Because diesel, the purpose of subsidizing diesel was to help the poor farmers and what to help the transportation industry so that the prices will be low. Prices of like a public transport will be low, prices of goods will be low because the transportation of goods will be cheaper. But what is happening is we are having these Innovas and all those fancy Innovas, even smaller now. There is a lot of big cars are coming out, SUVs, which are running on diesel. And in fact, they should never be allowed in the country in the first place. And but we need to phase them out because that's creating a lot of vehicular emissions, which impact on short-lived climate pollutants. For the agricultural sector, again, ban open field burning, not only agricultural, also even for the food, even for any type of waste. We see that even in the city of Kharagpur, in the town of Kharagpur, during especially this time of the year, with all the leaves that fall down from the trees and other stuff, along with the other plastics and other waste, I see people, like those workers, burning it in the morning just to get some heat because of the winter. So we need to, and then that produces a lot of air pollutants. Unfortunately, people are not aware. So that's a lot of capacity building needs to be done on that sector. But it's open burning, uncontrolled burning at low temperature, incomplete combustion. These are all the reasons why we get these short-lived climate pollutants coming into the atmosphere. So into the waste management sector, of course, we have to improve on recovery and utilization of gases and fugitive emissions, and leakage, reduce the leakage of the long-distance gas pipeline. And if we can separate and treat the biodegradable, because the biodegradable waste, organic fraction of municipal solid waste, which is the other way of calling it, if we can treat that in a controlled environment, whether it's potentially could be anaerobic digestion, AD plant generating those methane, and that methane can be used. So rather than having those fugitive emissions, we have a better control over the gases that is being produced. Of course, any organic waste, any organic material, when it is treated under anaerobic condition, it will produce methane. But rather than getting that methane exposed to the atmosphere, we can take the methane and make use of it as an energy source, and then of course that will get converted to CO2. So which is again the harmful gas, but it's a much less harmful as compared to methane. And theoretically, and in some cases, in some parts of the world, even in practically, those CO2 is even further captured in terms of the CO2 sequestration project. So there are ways to manage that. Unfortunately, economics doesn't make the case in many. That's why it doesn't get done. But potentially the technology is out there where we can capture the carbon and then do not let any carbon go into the atmosphere. So upgrade the wastewater treatment plant with gas recovery and the also there. In terms of the solid waste, as I was telling you earlier, if you go for the aerobic, you will have, of course, CO2, you will some effluent, some biomass. If you go for anaerobic, we'll have methane, CO2, again some biomass, some effluent. So there is a methane and CO2 is being formed, especially when you are doing aerobic and anaerobic treatment of organic waste. When you go to open burning, you have the other things being formed in terms of like a black carbon, in terms of the precursor gases, which will create tropospheric ozone, and those they do get formed in terms when we don't manage the waste properly. So that's kind of give you a quick idea about what is the short-lived climate pollutants, what are the sources of it, and how they relate in the waste management sector. What are the sources, especially from the waste management point of view, how these short-lived climate pollutants can be generated from the waste management activities. Now, so we know that it is being generated. Then the other, of course, the second thing is that how to know how much it is generated. Like what is the how to emission estimation, how to look at the emission measurement. So that's what we'll be talking about in next few slides. So there are different ways to do it. There are some modeling is there. There are, and we'll talk about these. So there are the standing chamber method. That's for in situ measurement of CH4 and CO2 flux rates. So that is also done. That the chamber is used. Flux chambers basically. Then there are IPCC model which can be used to estimate the emissions. There is a modified triangular method. There is a US EPA LNGM model is there, especially for landfill gas like estimation. So we'll talk about that. The static chamber method, you can have a stainless steel chamber for landfill gas collection. So you can put it on top of a landfill, and you can have it. You can have a temperature. You can measure the temperature. You put this on top of a landfill or a dump site. You have a gas sampling port, so you can collect the gas and measure the gas composition. And you can also have it connected to some sort of Treadler bag to get the volume coming out. So what's the volume of gas being produced? So you can get the volume of the gas, you can get the gas composition, which will be the gas quality. So that way we can say what is the emission, we can get the emission rate of methane or even H2S. If we say H2S being produced, we can even get the H2S, but H2S may not be directly related over here, so we'll just stick with methane. And you may have, of course, you will have some CO2, and depends, some cases you may see a little bit of carbon monoxide as well, depends on how the scenario is, not always. So this is where we can do like a standing chamber method, so you have to do some field work for that. And then there is another one which is the modified triangular method. Here you assume a first order decay, and then say that it follows a triangular pattern. The area of triangle is assumed to be equal to the volume computed using default methodology. And it assumes that degradation is happening in two phases. The first phase starts after 1 year of deposition and increases linearly up to 6 years. Then we have the second phase, where the rate decreases linearly and becomes zero after around 15 years. So that's it assumes that in 15 years most of the decay has taken place. That's not always true though, because we have seen in some of the landfills, even after 30 some years, still, because the initial landfills which were had that liner system in place and North America and Western European countries. So even those landfills today, which is nearly 35 years later, is still producing a little bit of gas. So it's not that gas production goes totally zero, because the things are not favorable many times for the waste to degrade. So, but using the gas volume and the base of triangle height, H, the peak value of methane generation, and other ordinates can be calculated. And then we have the other way of greenhouse gas can be estimated by IPCC model. It has a multi-phase model developed into nearly more than 10 years ago in the year 2006 for the estimation of methane generation from the entire countries, although it can be modified to estimate GHG's emissions from individual landfill sites. You can look at the regional waste generation rate, population estimate, look at the degradable organic carbon, fraction of degradable organic carbon, then waste decay rate, methane correction factor, and all those things. Because the waste decay rate also will change on where you are. If it's in a very dry zone, the waste decay rate will be different. If you are in a wet area, the waste decay rate would be different. And if you start operating your landfill as a bioreactor, again, the decay rate will change. So those are a lot of factors that goes into there, and that can be used to look at the greenhouse gas emissions from IPCC model. And that's the IPCC model is for not only for the landfill sites, so it could be for other places as well. This LandGEM has been developed predominantly for the landfill site, and it's a model developed by US EPA, United States Environmental Protection Agency. It's available actually for free. You can download this model. Some of you may be familiar with that. And if you're not, you can just Google and download this particular model and you can play with that. And what it does is, again, assumes a first order decomposition rate model, and based on empirical data from US sanitary landfill, they have, so better the input data, of course, the better the quality of estimate. So, and this is what is the basic equation used, where you try to get the total estimate, the gas emission rate, and you need to have that landfill gas emission constant, which is the decay rate, potential methane generation capacity of waste, which is your L0, which is given in that equation. That's how much methane will be generated, like volume per mass that generate from that particular waste. T is the age of the particular waste that we are looking at the time. What is the age? Like 5 years, 6 years. And then Mi is the mass of waste placed at the time I. So the way it is done is that they take the model is you can take the entire year. So for example, year 2018. So 2018's waste together as one batch. So 2017 would be one other batch, 2016 would be the another batch, and on the time you will calculate based on that. So of course there will be some, you will assume that the waste placed on January 1st, 2017 and the waste placed on January 31st, so December 31st, 2017 is actually degrading at the same time. But since for some dates you will be kind of overestimating, for some days you will be underestimating, so eventually you should be okay in terms of the estimation. So that's this is the basic equation that is used, and the model which is available on the web, you can download. It's an Excel based, but the equation is there on the back. The Excel is very user friendly. The equation runs on the back side of the Excel spreadsheet, and it just gives you the value of the methane that is produced. So those are kind of different types of methods. So now if you look at some of these data with some of these papers which has been published over the last, say, 10 some years in terms of different landfill, the waste disposal sites, which is essentially landfill sites, and these are essentially dump sites, and how let's look at what people have reported on that in terms of so Chennai landfill, Jha and others in his research team in 2008, they have published this study where they found that IPCC method were chosen based on the composition of the waste. And they found out that the methane, carbon dioxide, and N2O emissions from the Chennai landfill were around 0.2 gigagram per year, 1.16, and 1 ton per year, respectively. So N2O is much less compared to the other two, but N2O is nearly 298 times more potent than CO2. So that's that is also there, and then there was some variability because of the heterogeneous nature of landfill and compaction across landfill gas emission fluxes. So they did find a lot of variation within the site as they go from one place to another place. Moore et al. Did a study in 2006 where they look at the Gazipur landfill, Gazipur in Delhi. They again first order decay model. They use the modified triangular method to do around 15.3 gigagram per year. So to reduce the greenhouse emissions from this landfill, we suggested to increase the oxidizing capacity of the top layer. So if you can we put some oxidizing capacity on the top layer, or collect the methane to flare it, if somehow you can do the collection and flaring, so that you can convert that to CO2. Then another study on Gazipur, Bhalaswa, and Okla, the gas samples were collected using closed chamber technique, at regular intervals, and then both summer and winter. Using GC, it was analyzed, and they found that 0.24 from methane emissions from all these three, Gazipur, Bhalaswa, and Okla, obtained as 0.24, 0.16, and 0.14 meter per year, respectively. So it also depends on the size of the landfill, what type of waste that is there, and how old the waste is when based on when you did the sampling. So they conducted that methane generation on landfill in summer was much more than the winter. That's not surprising, because in the summer months, the microbial activity is more as opposed to what you will see in a typically winter month. So gas, here the other one, this Rawat and his team, they did some work in 2008 where the gas was collected using the Perpex chamber, and they found that average value of around 0.21 T tetragram per year. So Kolkata, Delhi, Dehradun, Bangalore, Chennai, and Ahmedabad, Chennai observed to be highest, could be because of the rain, nice, better weather conditions in terms of producing methane gas than others. That could be one potential reason. And then similar studies in Indore, where they use both IPCC as well as the Lendium model, and they found it strict plus minus 10% within that 0.388 and 0.31. So that's what they predicted, that average temperature will increase by 2 degrees centigrade if we don't by 2030, and may go up to about maybe 3 to 4 degrees centigrade by 2080. So it's they've also found that waterlogging and dumping of MSW in open drains was also there. So that's in terms of different type of measurement techniques, and so the data which has been already, the measurement techniques have already been have been applied on the waste disposal sites. So of course, any technique always needs refinement and try to be more accurate as much as possible. More the data you collect, the better it is. So that's where we kind of getting into the scientific data management, especially from the waste management sector, since things are so heterogeneous. So even if you look at waste management, even to characterize the garbage, to get a good waste composition numbers, and it's highly heterogeneous. So it's a heterogeneous material, and then if you use a heterogeneous method to producing data, then that means we are adding lots and lots of uncertainty on the captured data. So then lots of statistics it's always involved. So it's multi-scale nature. We have a spatial scale, we have a temporal scale, especially when you're looking at something like a big landfill site. And then you may use tools of imaging and other stuff as well. So we can get a lot of data with hundreds of attributes, dimensions, or descriptions. So the challenge becomes is all these days we talk a lot about the big data. Big data, big applications, is scale. Now, more the data, you need to analyze those data. You need to handle those data, make sense out of those data. So there is a complexity, there is a multi-scale data, lots of dimensions, and many of these models have certain assumptions as well. They need certain type of information which is not available. So either you use some secondary data or you make your own assumptions, and that's added more complexity. And as I said, there's a lot of heterogeneity as well. So there are particular data semantic heterogeneity is there. So in terms of the uncertainty, what we try to do is we look at how to handle that. So it depends on how you interpret the source and sink category. There are other definition assumption. So you can start with something like an average value, use of simplified representation with the average value, for example, in terms of emission factors, and try to have a representative characteristics of a given population. Then go for uncertainty in the basic socioeconomic activity data. So there are some inherent uncertainty in scientific understanding of the basic process. So because even if you look at that methane is 25 times more potent than CO2, you look at different, these are all based on different model, which model has also again certain assumptions, and those assumptions, because scientifically our understanding is not up to the level that we are sure of certain, so we make certain assumptions, and we go by that. As we improve our scientific understanding, those we refine those assumptions and try to become closer to reality as much as possible. So these things are like in process. It's a dynamic process which is going on. So when we try to estimate uncertainties, we can do it by source category and for a national inventory. So we have to kind of develop a database specific to the individual country. So we need to do methodology and data source use. Whenever you're using a database, you're looking at the data, it's very, very critical to look at how it was collected and what kind of data source was used. And usually what we see that around 95% is confidence limit is often regarded as an appropriate for the range definition. So you check the upper confidence and lower confidence. Its uncertainty ranges can be used as classical analysis of the Monte or the Monte Carlo technique. Otherwise, we can have some expert panel do that. So there are ways to combine uncertainty statistics. Our statistics friends have come up with a lot of improvement in that subject area. So we have we can combine uncertainties, we can derive overall uncertainties from the combination of factors and activity data. Here, for example, when you're looking at the combination, you have you have UE and UA, which is the emission factor, and then the activity of the area. So that's with that we can look at the different type of uncertainties and try to combine it together. So in same thing here, but in the emission units, they can be combined where you look at the UT and then you have the central estimate of the emissions in the same source category. So that's how essentially these uncertainties could be incorporated. Uncertainties will be there. It's also in the way since the sampling, how to get the representative sample, how to get to collect the data, analysis of the data, inherent some instrumental error, human error, all those things gets involved there. So that's why we have to work with the statistical tools to address those uncertainties associated with that. So in summary, what I was trying to explain, and I hope I was able to do that, we are looking at short-lived climate pollutants because they are causing around 40 to 45% of the global warming. That's what, and the rest 55 to 60 is carbon dioxide, which is known as a long-lived climate pollutants. And as introduced, it's a black carbon, tropospheric ozone, methane, and hydrofluorocarbon. So those were there. It's critical, showing the rate of climate change over the next several decades. And measuring and monitoring methods are there. It is being developed. It is being used. It's also being improved upon, including the data management and the data uncertainties. And with all the newer computer power that we have, data analytics that we have, things are actually, there's a lot of improvement that is being happening. There's a lot of scope for further research and development in this particular area. So with this, I would like to close my presentation. There are some references, and then of course, this is my contact information here. So I'll hand back to Kaushik.
Thank you, Professor Dubey, for this detailed presentation and your insights on today's topic. We have a few questions as a part of today's webinar. From our audience from the municipalities, in terms of setting up monitoring stations for black carbon and methane monitoring, how mature is the technology like ethylometers to be set up on a municipal scale?
So can you repeat the question again?
So in terms of setting up monitoring stations for black carbon and methane levels at the municipal level, how mature is the technology in India? For instance, ethylometers, which could be used to monitor levels of black carbon.
As far as I know, like I haven't seen many municipalities using them. It's mostly used by, say, from time. It's not a continuous monitoring. It will be sampling events happening from time to time. So you go out and sample it, and then you bring the data, and then you try to estimate the total values based out of that. 24 hours continuous monitoring might be happening in certain areas, but that I'm not aware of. So I don't, in my based on what I know, I don't see a continuous monitoring happening as of today. Although in some other places it does, but in Indian scenario, if it's happened, I'm not aware of that.
Another question says, in terms of policy in India, How is it placed in relation to measurement of short-lived climate pollutants? I think they mean from where does the policy-related mandate or regulations pass on in terms of short-lived climate pollutants measurement?
Yeah, so in terms of that, see, each of these four short-lived climate pollutants, they are addressed as part of the climate and clean air coalition to reduce them as part of the CCAC. And CCAC does comprise of developing and developed countries, including UNEP, UNDP, European Commission, World Bank. So we are partner of that. And so we are so we do have to reduce this short-lived climate pollutants as part of this climate change initiative globally that India is part of. And so it is there. So if that's the question, yes, we have to do it. But how to do it in terms of course, as if you from the waste management sector, which I am more familiar with. So if you think about from this Swachh Bharat mission or this new waste management rules 2016, where we have been talking about promoting anaerobic digestion like biomethanation, where essentially what is happening, these are mostly either fugitive emissions or emissions which we are letting it go. So either of those two. So in case we can control those emissions, so which if we can implement our rules in the waste sector, that's where if we, for example, the food waste, three-way separate collection. Again, for the waste management, whenever we start talking about waste management, we ultimately we go to source segregation. So if we start doing this source segregation where we can have this food waste collected separately and do biomethanation, or even you do a proper composting where you have nice airflow so that you don't produce carbon monoxide, you produce carbon dioxide. And of course, NOx could be an issue there, which will lead to tropospheric ozone formation. But those are the ways, like a proper implementation of the rule and doing the practices in a correct way, in a scientifically correct way. Right now, most of the places, even the compost system is not working like a compost system. Our compost is not reaching the good quality. And we don't have many landfills. We don't even have the gas collection system. So there is no fugitive emissions. It's all just all emissions. So there is just getting into the atmosphere. So is that answers that?
Yes, pretty much. Yes.
Okay.
The third question mentions the current haze problem experienced by Mumbai is due to PM levels produced due to vehicle emissions. However, the vehicle emission was always been there in Mumbai. Why is the hazy atmosphere seen only in the past few years?
Good question. I'm not sure about the exact. It could be the combination of some other. I'm not like a air expert of that particular area, so I don't have a direct answer. I would say that it could be because of combination of course. I don't know how is the winter. I'm not that familiar with the Mumbai area as of now in terms of different weather pattern. But what I would suggest probably it's because of there are some recent like a fire on the landfills there as well. So that and then vehicle is of course every time vehicle is increasing. So we have increase in number of vehicles in every city, including in Mumbai. There was a lot of landfill fires in recent times, but these are all my based on kind of what could potentially be leading to it. But I'm not saying that these are the only reason over there. But this could be some precursors leading to that.
Yes. So a couple of more questions before we close for the day. How can leachate produced by the landfill be collected, used, and processed? Is one other question which has come in today.
Okay, so that's a different, not today's topic, but we can always answer that. Leachate, as you know, leachate is essentially the water which is either the rainwater which has percolated through the garbage, or you have the water which is produced as a part of degradation of waste. So both of them together is what you have leachate being produced. So depending on the type of garbage you have in that landfill, you will have the leachate quality will depend on that. And what is the composition of the leachate? So how it is to be collected? Of course, we need to have a leachate collection system. So if you're talking about an engineered landfill, of course, will be a leachate collection system and all that. If it's an unengineered landfill, so somehow we have to, I guess the question is more from the dump site rather than from the engineered landfill, because engineered landfill, as we know, has to have a good leachate collection system, good gas collection system, and a stormwater management system. Yes. So these three are the most important part in terms of the engineered landfill. For dump sites, there have been, for example, in Delhi and some other places, they have tried to, at the bottom of the landfill, they have tried to channelize a little bit of, make a small channel where the waste, they can get the flow of leachate out and then collect it in terms of some sort of pond. You can line those ponds, or you can put it in some sort of if you have the lime pond, you can do some treatment, you can have an aeration going on if you have the space available. Otherwise, it needs to be collected and send it for the treatment plant. Again, the treatment plant, if the leachate is only the municipal solid waste, no big chemicals there or no heavy metals there that much, it can be treated at the wastewater treatment plant. So it's or you can have a separate leachate treatment plant.
Right. One last question before we close for the day, and this is with relation to black carbon being generated from kitchen-borne pollutants. I suppose it is because of the slide which showed that there are black carbon sources present within the house, which is responsible for indoor air pollution.
Yes.
The question says, how much black carbon is responsible for this as a part of indoor air pollution?
So if you think about, especially the main source of black carbon, of course, as we said earlier, it's the open burning of biomass and the residential burning of solid fuel. So when we have coal, wood, dung, or any agricultural resource, any agricultural residue, when we burn them, they do produce black carbon, and especially if you go to the rural area in those villages where the kitchen hardly has any window as well, maybe a small window. If I remember my like village when I used to see that, where we will have during the long time ago, more than 3 decades ago, when we will have those wood being burned or even the coal. And on the side of the wall, you will see all the black stuff in there, and also on the top ceiling, you will see those black stuff. So they do generate black carbon, and there has been a lot of studies done on that area in terms of this cooking fuel, burning of coal, wood, and in Indian setting. And the amount of indoor air pollution that is just causing that health impact on female population, who are mostly spending their time in that kitchen area, and also on infants, because usually you have these are the two set of population which you will see mostly in kitchen: infants, because they want to be closer to their mom, and moms who are doing the work in the kitchen most of the time. So they have been like a lot of studies have been done on health impact from the black carbon to these. So it's a significant impact in terms of burning of these fuel in a kitchen setting, especially if it's a non-ventilated. It's not properly ventilated that causes that. And there are a lot of reports out there on this particular aspect from different, even WHO and other places.
So we have one more question, Professor Dubey, before we close, if that might be fine.
Sure.
Industrial cities like Mumbai and Delhi can blame industrial and vehicular pollution for their plight. Why are less industrial cities like Patna facing pollution issues in the same proportion? Is inefficient waste management somewhere in the picture for this? is the question.
Yes, I would say even in Patna, it's of course inefficient waste management is in the picture. I personally have seen in just near Patna city the municipal workers burning garbage. The municipal workers burning garbage by themselves. So because it's a bulky, especially those styrofoams. I have a video of them burning styrofoams along with my colleague. We were visiting along with a colleague from IIT Patna while we were looking at some of the waste management activities in Bihar. So it's with the open burning of garbage, of course, that is creating problem. And the vehicular emissions, I would say, although Patna is maybe not that much vehicle density as you will see in Delhi or Bombay, but still, even our smaller cities and towns, the vehicles are increasing. We have lots of vehicles now coming into the smaller cities too, including Patna is not that small. So you see that vehicular emission is a factor. And then there is a lot of dust. That's another big area. The construction industry. When you have the construction industry, all those dust and other things created from the construction industry, those are also creating the pollution problem that you see over there. In terms of what you get in airborne, of course, you have waste plastics and other things getting into your drains and choking of the drain, and then you have the stormwater problem, and those issues are also there. But in terms of airborne, I would say waste management, vehicular emissions, construction activities, during that hot weather in Patna area, that the wind, that we call it loo, and that also creates a lot of, you will see a lot of dust coming into the, gets airborne, and that creates a lot of pollution as well.
Well, I think that answers the question. Thank you once again, Professor Dubey, for your time and the detailed thoughts on measurement and monitoring of climate pollutants in the waste sector. Thank you all for tuning in into this webinar. Thank you, sir. Thank you for your time.
Thank you. Thank you.